Welcome everyone, and thank you for joining me today. We're about to dive into a fascinating topic related to building geometry. On this first slide, I'll introduce some basic concepts. The focus is on the geometry of a typical room layout. Each room has a floor area of 4 by 5 meters, which gives us 20 square meters per room. Since there are 8 rooms, the total floor area sums up to 160 square meters. The height of each room is 6 meters, and we'll be using a watts per square meter approach to keep things straightforward and efficient. Keep in mind, the tall ceiling height is implicitly factored into our safety considerations. This overview will set the stage for the detailed analysis to come. Let's take a closer look at the peak cooling load, with some transparent assumptions to clarify our approach. For small rooms in KSA, we typically use a quick, specific load range, which is between 120 and 150 watts per square meter. This range accounts for moderate to harsher solar and internal gains, so it helps us estimate the cooling needs more accurately. Now, to calculate the cooling load, we use the simple formula. Qcool equals the area times Wm2. For example, in the low case, if we assume 120 Wm2 and our room area is 160 square meters, then the load is 160 times 120, which equals 19.2 kilowatts. That's roughly equivalent to about 5.46 tons of refrigeration. On the higher end, with 150 Wm2, the calculation becomes 160 times 150, resulting in 24 kilowatts, or approximately 6.82 TR. When making our design decision, we opt for the high case, using 24 kW or about 6.8 TR, because it provides a safety margin. This way, we ensure the cooling system will handle the maximum expected load reliably. So the key takeaway here is that by considering the high load scenario, we stay safe and ensure comfort and performance. Let's talk about the heat rejected at the condenser, which we denote as Qreg. This value depends on the cooling load, Qcool, and the coefficient of performance, or COP. The formula here shows that Qreg equals Qcool multiplied by 1 plus 1 over COP. Now, at peak conditions, we typically take a COP of about 3 for small direct expansion systems operating at high ambient temperatures. So, plugging that in, the factor becomes 1 plus 1 divided by 3, which simplifies to approximately 1.333. Using this factor, for the low-case scenario, we multiply the cooling load of 5.46 tons by 1.333, giving us about 7.28 tons, or roughly 25.6 kilowatts. For the high or design case, where the cooling load is 6.82 tons, multiplying by 1.333 yields approximately 9.1 tons, or around 32 kilowatts. The key takeaway here is that the heat rejected at the condenser increases proportionally with the cooling load, adjusted by this factor based on COP. This is important because understanding the condenser load helps us size the equipment correctly and ensures efficient operation under various conditions. Remember, these calculations are vital for designing systems that can handle peak loads and operate efficiently throughout the year. Let's take a look at the outdoor and condensing targets for air-cooled systems. In our design environment, we're considering an ambient temperature around 46 degrees Celsius, which is typical for Dammam. This high ambient temperature plays a critical role in determining our condenser performance. Now, when selecting our approach temperature difference, or delta T, we aim for approximately 12 Kelvin. This means that our target condensing temperature, T-cond, would be around 58 degrees Celsius. These parameters are essential because they influence the efficiency of our cooling process. By understanding the ambient conditions and setting appropriate temperature differences, we ensure our system operates reliably and effectively under the hottest expected conditions. This connection between outdoor conditions and condensing targets helps us optimize our design for real-world performance. When selecting an air-cooled condenser, it's important to focus on a few key factors. First, you want a coil and fan setup that can reject at least 9.1 TR, which is roughly equivalent to 32 kW of heat. This capacity needs to be maintained under specific conditions, specifically at an ambient temperature of 46 degrees Celsius. Additionally, the target condenser temperature, Tcond, should be 58 degrees Celsius or lower, which corresponds to about a 12 Kelvin approach. This is crucial because it ensures the system operates efficiently and stays within safe temperature limits. If your initial condenser choice requires very high fan speeds to meet these conditions, or if it causes Tcond to rise above 58 degrees Celsius, then it's wise to select a slightly larger size. Going one size up can help reduce the fan load and keep the temperature within the optimal range. Remember, selecting the right condenser isn't just about meeting capacity. It's about ensuring reliable performance under the worst-case conditions we might encounter in operation. Let's take a look at some quick airside checks that can really make a difference in system performance. First, there's the airflow thumb rule, roughly 1,000 cubic feet per minute, or CFM, per ton of rejection. So, for example, if you have about 9.1 tons, that translates to approximately 9,100 CFM, which is around 15,500 cubic meters per hour, flowing through your condenser coils. Next, I want to emphasize face velocity. Keeping this at or below 2.5 to 3 meters per second is crucial. Why? Because it helps maintain efficient heat transfer and prevents issues like airflow noise or pressure drops. And speaking of noise and energy, investing in a larger coil or increasing fan area can be very beneficial. A bigger coil or more fan area reduces the condensing temperature, which in turn improves overall efficiency. These checks might seem simple, but they are essential for ensuring your system operates reliably and efficiently, supporting the overall goal of optimal performance and energy savings. Let's look at the system layout options for supporting 8 rooms. One approach is to use a single outdoor multi-split or VRF branch, which can serve all 8 rooms. The key advantage here is that diversity helps, meaning the system isn't working at full capacity all the time, which improves efficiency. Alternatively, we could opt for 2 smaller systems, perhaps one on each floor, with around 3.5 to 4 tons of refrigeration each. This setup offers some benefits like redundancy, so if one system needs servicing, the other can still maintain comfort, and it also shortens the piping runs, which can simplify installation and maintenance. No matter which option we choose, it's crucial to ensure that the combined condenser capacity can handle the target rejection at 46 degrees Celsius ambient temperature. Specifically, we need to meet a 9.1 ton rejection capacity. This ensures the system performs reliably even under high outdoor temperatures, maintaining efficiency and comfort. Connecting these points, the main takeaway is that both options have their merits, but the key is to match the condenser capacity to the cooling load, especially considering the climate conditions. This helps us design a system that's both effective and resilient in serving all 8 rooms. When reviewing the datasheet, there are several key factors to focus on to ensure you choose the right equipment. First, pay attention to the rated heat rejection at a condensing temperature between 46 and 58 degrees Celsius, which is different from the ARI nominal rating. This gives you a more realistic expectation of performance under actual operating conditions. Next, look at the number and size of the fans, because these directly impact the total airflow and the sound power generated. Larger or more fans can mean higher airflow, but also potentially more noise, so balancing these is important. Then examine the coil details, the coil area, the number of rows, fin density, and any coatings. Especially in coastal environments, corrosion protection becomes critical, so coatings that resist corrosion can extend the lifespan of the equipment. Finally, review the electrical specifications, such as the fan kW, MCA, and MOP ratings. Also, consider the controls, like whether the system has fan staging, variable frequency drives, or head pressure controls, because these features can optimize efficiency and performance. All these factors are crucial because they directly connect to the overall reliability, efficiency, and longevity of your HVAC system. Locking onto these details during the datasheet review helps ensure you select the equipment that best fits your application's needs. Let's wrap up with a quick summary of the key numbers we've discussed. We have 8 rooms, each measuring 4 by 5 by 6 meters, which gives us a total area of about 160 square meters. When it comes to cooling, our peak design load is approximately 24 kilowatts, which is roughly equivalent to 6.8 tons of refrigeration. For the condenser, we need to select a duty of around 32 kilowatts, or about 9.1 tons of refrigeration, especially when operating at an ambient temperature of 46 degrees Celsius. We're targeting a condenser temperature of around 58 degrees Celsius, which provides about a 12 Kelvin temperature approach. And finally, to ensure effective heat rejection, we need an airflow across the condenser of roughly 9,100 cubic feet per minute, or about 15,500 cubic meters per hour. These numbers are essential because they tie directly into designing an efficient and reliable cooling system that meets the overall project goals.